1638, Tuscany. Galileo Galilei analyzes projectile motion. He proves the path is a perfect parabola, but he knows it's only true in a vacuum. In the real world, the air fights back. To predict this, you need to calculate forces that change every single instant. But no one had unified that math. The tool was missing. That limitation meant we were firing blind. For 2,000 years, humanity could measure static shapes, the area of a circle, the volume of a pyramid, the angle of a star. But the shape of motion itself, invisible, unmeasurable. This is where the war began. One invention connects ancient Greece, Newton's Principia Mathematica, in the AI you use every single day. For most of human history, we were missing a tool, a mathematical language, a computational framework. Without it, the modern world you know could not exist. Relativity, quantum mechanics, space travel, machine learning. The question is simple. Who invented calculus? The answer is one of the ugliest, messiest disputes in the history of science. 250 BCE, Syracuse, Sicily. No one knew how to calculate its exact area. So, Archimedes of Syracuse tried a radical approach. He drew a hexagon inside the circle and calculated its area. Close, but not exact. 12 sides, closer. 24 sides, even closer. 48 sides, 96 sides. Archimedes realized if he kept increasing the sides, forever, the polygon would become the circle. The first glimpse of infinity is a tool, but he couldn't command it. For 2,000 years, the problem remained unsolved. Until someone changed everything. Before we meet Newton, we need to understand the world he inherited. By the 1600s, Galileo Galilei, Johannes Kepler, and René Descartes were asking a new kind of question. Not just, what shape is this? But, how does this change? How fast is this planet moving, right now? Not average speed, instantaneous speed. Speed at one exact moment. Here's the paradox. If the moment is frozen, then there's no motion. So how can there be speed? The ancient Greeks called this Zeno's paradox. Aristotle debated it for centuries, but no one could solve it mathematically. In 1665, the bubonic plague swept through England. The Great Plague of London, 100,000 dead. Cambridge University closed. Students were sent home. One of those students, a 22-year-old named Isaac Newton. He was alone. No teacher, no guidance, just a notebook in a plague outside. No one watching, no one correcting him. He was brilliant, but he was also unfinished. He had studied Euclid's Elements and learned Descartes' La Geometrie, but there was something missing, a gap in the mathematical language he knew. He wanted to solve the motion of the planets, Kepler's elliptical orbits. He wanted to understand gravity, universal gravitation. But without this, there would be no Newtonian mechanics, no astronomy, no engineering, no modern world. But every tool he had failed. Let's try to solve it the old way. Geometry first. You can use Euclidean geometry to describe orbits if they're perfect circles, but Kepler had proven that planets move in ellipses, and ellipses, they're messy. Geometry fails. So what about algebra? You can write an equation for an ellipse, but how do you find the instantaneous speed of a planet at one point on that curve? Average speed is easy, distance divided by time. But at a single instant, time is zero. At dividing by zero, it breaks everything. Algebra fails. Newton was stuck, and this is where most people would give up. But Newton, he changed the question. He stopped thinking of curves as frozen shapes. He started thinking of them as flowing. Imagine a point moving along a curve, not jumping from place to place, just flowing, like water. Newton called this flow a fluxion. And he asked, what if we could measure the flow itself? Zoom in on any curve close enough and it starts to look like a straight line. And straight lines are easy. They have a slope, rise over run. So, Newton said, what if we zoom in infinitely close, so close that the curve becomes a line? Then, the slope of that line is the instantaneous rate of change. But how do you make that rigorous? How do you actually calculate it? Newton invented a process. Start with a curve, y equals x squared. Click a point, x. Move forward a tiny amount. He called it O. Calculate the change in y, divide by O. You get 2x plus O. Now, let O shrink to 0. And you're left with 2x. Newton called this the fluxion. Today, we call it the derivative. In Leibniz notation, dy over dx.
But Newton didn't stop there. He realized something more. Remember Archimedes filling a circle with polygons? Newton did the reverse. He filled the area under a curve with rectangles. Each rectangle has width O and height y. Add them all up. As O approaches 0, the number of rectangles approaches infinity. This is the opposite problem. Instead of measuring the slope of a curve, you're measuring the area under it. Newton called this the fluent. Today, we call it the integral, the Riemann integral, the definite integral. So now Newton has two tools. The derivative measures change, the integral measures accumulation. But he's still stuck. Why? Because these two problems seem completely unrelated. Finding the slope of a curve and finding the area under a curve, what do they have to do with each other? Everything. Turns out, Newton wasn't the only one working on this. More than 2 centuries before Newton, in Kerala, India, a mathematician named Madhava of Sangramagada discovered infinite series expansions for pi, sine, and cosine. The Madhava series, the Kerala school. He understood that infinite sums could represent curves. This is proto-calculus. But it remained a collection of techniques, not a unified system. And in Europe, there were others. Pierre de Fermat, Bonaventura Cavalier, Isaac Barrow. Was calculus already discovered? Was Newton just the guy who wrote it down? No, because what Newton did was different. He unified everything. Newton unlocked the fundamental theorem of calculus. It's one of the most beautiful ideas in the history of mathematics. The theorem says this: the derivative and the integral are inverses. They undo each other. If you take the derivative of a function and then take the integral of that result, you get back to where you started. But more than that, it means these two problems, finding slopes and finding areas, are not separate problems. They're the same problem. This was the moment calculus became inevitable. This wasn't just a solution, it was a unification. Watch the point flow along the curve. At every instant, it has a velocity, that's the derivative. And as it moves, it sweeps out area beneath it. That's the integral. The faster it moves, the more area it sweeps. The slope controls the area. The change controls the accumulation. Two mysteries that haunted humanity for 2,000 years were secretly the same mystery, the same problem. Newton had solved it. He'd built a language for change, a language for motion, for growth, for everything that flows.
He kept it secret for 20 years. Because while Newton was working in silence in England, someone else in Hanover, Germany, was doing the exact same thing at the exact same time. Gottfried Wilhelm Leibniz discovered calculus independently. Same ideas, different notation. Leibniz published first, 1684, Nova Method. Newton published later, 1687, Principia Mathematica. But he used the language of geometry to hide his secrets. Newton accused Leibniz of stealing the calculus priority dispute. Leibniz fired back, "You kept it secret for 20 years. How could I have stolen it?" He had a point. Then Newton did something unforgivable. He was president of the Royal Society at the time, and he secretly wrote their investigation report himself and signed it, condemning Leibniz. Letters flew across Europe. Johann Bernoulli, the Octa Eruditorum, accusing of plagiarism, national pride on the line, careers destroyed. It was ugly. The irony, they were both right. They both invented calculus, independently. But only one notation survived. We use Leibniz's symbols today, dy dx, integral. The integral is a stretched s for summa, Latin for sum. Why? Because they were just better, more intuitive, more flexible. Newton won the battle, but Leibniz won the war. But here's the problem. Calculus worked. It predicted planetary orbits, calculated trajectories, unlocked physics. But it wasn't perfect. Because even Newton didn't fully understand what he had created. The problem was infinity. Newton said, "Let O become infinitely small." But what does that mean? Is O zero? Or not zero? If it's zero, you can't divide by it. If it's not zero, you can't ignore it. So which is it? Newton couldn't answer that. For 150 years, calculus was the most powerful tool in science, but its logical foundation was shaky. If calculus collapsed, physics would collapse with it, and so would the modern world built on it. Philosophers mocked it. Bishop George Berkeley called derivatives ghosts of departed quantities. Calculus worked, but no one knew why. And then the cracks began to show. But it didn't collapse. It took two more geniuses to fix it. Augustin Louis Cauchy and Karl Weierstrass. They rebuilt calculus from the ground up. They formalized the concept of a limit, the epsilon-delta definition. They made infinity rigorous. No more infinitely small, instead, arbitrarily close. You don't let O become zero, you let it approach zero, and you prove that the result stabilizes. This is the calculus you learn in school today. Clean, rigorous, beautiful. It took 200 years to get there. Because mathematics isn't just about being right, it's about understanding why. Newton built the engine, Leibniz built the interface, Cauchy and Weierstrass wrote the manual. When I first understood this theorem, it didn't feel like math, it felt like magic. That's how science works, one generation at a time. So, what happened next? Once humanity had the language of change, what did we do with it? Euler used calculus to describe vibrations, fluid flow, and light. Lagrange reformulated all of mechanics. Gauss applied it to electricity and magnetism. Einstein used calculus to describe curved spacetime. Every rocket launch, every bridge, every medical scan, every weather forecast. But the story doesn't end there. Calculus also powers artificial intelligence. Modern large language models, image generators. Every time you train a neural network, you're teaching it to minimize error, the loss function. That process is called gradient descent, backpropagation, powered entirely by derivatives, the chain rule, partial derivatives. The derivative tells the network which way is downhill, so it takes a step, adjusts its weights, moves closer to the answer. Again and again, billions of times. A real neural network lives in a space with billions of dimensions. The network is trying to find its way in a landscape we cannot visualize. Navigating billion-dimensional space, one derivative at a time. And it works. Remember Archimedes? Approximating a circle by breaking it into tiny straight pieces. A transformer neural network is doing fundamentally the same thing. From pixelated circles to artificial intelligence. Over 2,250 years apart, the same idea. It's all connected. Calculus is the language of change. 2,000 years. One idea. Infinite consequences. This is calculus.